divided by 2 times the cosinus of 2 theta and the Ps, which is now the shear component of the vector on that plane, is sigma 1 minus sigma 2 divided by 2 times sinus of 2 theta. And this is a very interesting way to express the normal and the shear stresses on this plane, because maybe you remember that in quantitative geology course last year, we made a plot of the sinus of an angle against the cosine of the angle. If you plot the sinus of an angle against the cosine of an angle, what you get is a circle. So this here is the equation of the circle. And this circle is called the Mohr circle. It was invented by a German engineer, Otto Mohr. And the Mohr circle is known and taught to many, many students in the RWTH in all kinds of different engineering sciences. Even our video cameraman knows about it. And to make this a little bit easier for you to grasp, I make a couple of very simple little simulations for you. Again, it is part of this spreadsheet. It is part of this little spreadsheet program that you can download and you can play with. And I hope it will work. Before I show you this little demo, are we going to clean the air filter? So here is a drawing of the plane, is the stress vector on it, decomposed into normal and shear stress. And here is this stress tensor made out of this little matrix, and the way that you calculate the stress on the plane. Okay? So here in this sheet I use S instead of P, but the derivation is really the same thing. And if you now take the normal stress and the shear stress on this particular plane, and you plot them against each other, normal stress and shear stress, and you get a circle, and this is the Mohr circle. Now go to my demo. And what I've done here is I made this little matrix 1, 1, 1, 2, 2, 1, which is the same as 1, 2, and 2. And I put in here 0.5 and 2. As numbers. Of course, you can put in all kinds of numbers if you want. But now you cannot put in numbers here which are different from that. That is not allowed in the stress. Otherwise, it's very simple. And here is the plane normal, oriented at this point 90 degrees to the first axis. Okay, so here's my plane. This is my plane normal. And the vector is this green line here. It is normal through my plane, and it is exactly 2 long. This was the second simple exercise that I showed you. And now if I put in here 45 degrees, enter, then I get my plane at 45 degrees, this is normal like that. This is the plane, this is the plane normal, and here is my stress vector calculated. And what you can see is that if I turn around my plane, then the tails of the stress vectors on the plane lie in an ellipse. This is called the stress ellipse. And of course, In the previous lecture, you have seen that a very simple matrix transforms the circle into an ellipse, so it is not a surprise that this happens. And now I can put any number here if I want. For example, I put 0.8 here, and 1.1 or 1.2, and I get an ellipse which is almost a circle. Of course, this is 0.8, this is 0.2. I can still go around and I get the stress. And what is very important to realize that in almost all of these orientations, the stress vector is not perpendicular to the plane. It is mostly a little bit misoriented. And this misorientation of the stress vector leads to earthquakes, because it has a component that can shear. Now what I've done here is I calculated the normal component and the shear component of my stress vector. These two numbers are the coordinates of my stress vector on the plane. And then what I've done is I've plotted this normal component and shear component against each other. And I've opened this figure now. Here it is. The shear component is this much. The normal component is this much. This is my plane. In the new diagram, it is a point. And if I turn around my plane, for example, I give it another orientation like 80, then I see that my plane turns around, the tail of the stress vector remains on the ellipse, and here my point is traveling around in a circle. What is very interesting to note, and you can play around with it if you downloaded this spreadsheet, that this point on the circle travels twice as fast as this is rotating. And the reason for that is that we have these 2 theta in the formula of the derivation. Okay, so I will be very brief with this one now. In the main lecture I will talk about it a little longer, but you can download it, and I would really invite you to use this tool to understand the components of stress. Maybe one final example. What happens if I put 1 and 1 into these two S11, S22 cells? In that case, my stress ellipse becomes a circle, and because of that, my Moore circle becomes a point, because it has shrunk into very, very tiny place, very, very tiny area. Okay? So this is the situation of the stress which you have underwater. If you go diving or swimming underwater, the stress on every direction is the same. This is what is called hydrostatic stress or isotropic stress. If the stress is anisotropic, like in a solid, then you have the stress ellipse and the Moore circle. Okay, so now let's take a few minutes break and then continue with the lecture. Okay. To summarize, I've done up to now derived the basic equations to describe stress in a very small unit. This is homogeneous stress. Every point is the same. In fact, the derivation really goes about infinitesimally small cubes. So we are talking about stress in the point. And what we have learned is that there is this matrix that transforms the normal vector on the plane into the stress vector on that plane, and that all these stress vectors define an ellipse, which is really just a collection of the tails of these stress vectors for a given collection of values on this matrix, we have learned that to get equilibrium, this one and that one have to be the same, otherwise my little cube starts to spin. And that if you now take the normal and the shear component of that stress tensor for all the different planes possible, and you plot them, that you get a circle. So this stress in a point, which is really the collection, stress vectors and all different possible planes, can be represented by this Mohr circle diagram. And in the future lectures, I really expect you to understand this in some basic way, because I'm going to draw a lot of circles, a lot of Mohr circles during this course. Okay. I started one of the slides in this lecture by saying that normal stress and shear stress are very important ways to plot these stress components, because it is the basis of friction. So now let's talk a little bit about friction. Here is a picture that should surprise some of you. It is a picture which was taken with a camera without any photoshopping. And the way we did this is that we did it on a very steep slope. So Frank, who used to be one of our students, is actually standing there. He's leaning backwards, and the slope he's standing on is this thick. So the only thing I did is I rotated my camera. And the reason why this is possible is because there is a lot of very good quality friction under his feet. So what is friction? One of the basic laws of physics, mechanics, is that if you have two little blocks, and there is no gravity in this particular case, but there is just this force, and this angle, then the blocks will slide if there is a critical angle between this force vector, and it doesn't really matter how big the force is. The force can be big or small, it is the angle which determines whether you get sliding or not. And this F, or if you want to divide it by the area, then it becomes the P, the stress vector on the plane. It can be decomposed into a normal component and a shear component. We have seen that before. And now, to define whether the two blocks are going to slide or not slide, all you have to do is you have to make this diagram where this is the shear stress on the plane and this is the normal stress. In an alternative notation from the P's that I used for the derivation, people also use the tau and sigma n notation. Then what you will get here is that there's this line with this critical angle, which is called the friction angle. And if the stress on the plane is below the line, everything is stable, nothing will happen. If you're on the line, you will start sliding, and this part of the diagram is impossible. You cannot get there, because the moment you reach the line, you will start to slide. So this is the very, very simple law of friction. To get this a little bit better in your understanding, I made a very simple exercise. So here's the question. I have a base, like a street, and there is a big sandstone block. That is 1.5 meter high, and I want to move it over a horizontal surface. What I know is that the density of the sandstone is 2,200 kilograms per cubic meters. What I also know is the friction coefficient, which is the tangent of the friction angle. It is 0.85. The acceleration of gravity is 9.8 meter per second squares. And what I want to know is the shear stress, tau, which you need to move this block. So imagine it is a huge block of sandstone, 1.5 meters high. It's enormous, it's very, very heavy. And I'm asking you the stress